So what is the hybridization of a carbon in an alkane? First, what is an alkane? Looks something like that. And when we take a closer look at every carbon, there's going to be implied hydrogens. So we have 4 groups around every carbon in an alkane, making that sp2 hybridized. Now problem 2, that molecule right there got cut off. It's not very clear what it is. And so what is not a representation of 2-methylbutane? Well, first, let's just ignore this even exists, okay, because it's cut off. How would we approach this problem? Well, I would just draw out 2-methylbutane, okay, and so that would be 1, 2, 3, 4. That's 2-methylbutane. Now that structure that I drew right there matches that guy, so that's 2-methylbutane. If we look at this condensed formula right here and we draw it all out, we see we have those 2 carbons right there, so 1, 2. Then it's attached to a carbon, and at that position we have, let's see here. So if we number the carbons, let's do that this way, shall we? That's carbon 1, that's carbon 2, that's carbon 3. So 1, 2, and 3. And what's attached to carbon 3? 2-methyl. So 1, 2. Okay, and so if we zoom out there, you will see that those 2 structures right there, this guy and this guy, are the exact same thing. And then we take a look at this guy, little expanded out Lewis structure here. I'll just convert it to a zigzag so I can make a apples to apples comparison here. There's 2 carbons right there. That carbon right there is now this one. And then attached to that circled carbon was 2 methyls. So you'll see that all 3 of these structures right here are the exact same thing, 2-methylbutane. And whatever this guy was at the very end is the incorrect. It's not 2-methylbutane. What structure is it? I don't know, because the image is completely cut off. But that's how you would approach that problem. Question 3, which of the following compounds has only primary and secondary carbon atoms? So now we just have to draw out each structure. Okay, trimethylpentane. So the way I approach that, the pentane means 5. So I'm just going to measure out 5 right from the start. 2, 3, 4, 5, like this. And if I number the carbons, 1, 2, 3, and I see that it says that there's a 3 methyls at position 2 and 3. There's 1 methyl here, and then 1 methyl there, and a second one there. Just like that. So if I clean that structure up, okay, for the 2,3,3 trimethylpentane, does that make sense? 2, 3, 4, 5, boom, like that. That's the structure we would get. 1, 2, 3, 4, 5. I'm just double checking the longest carbon chain. So there's that molecule. Let's see, pentane would just be 2, 3, 4, 5. So that's molecule C. This is molecule A, molecule B, 2-methylpentane. So draw out 5 carbons because of the pent. 2, 3, 4, 5. And then at position 2 we have a methyl. So that's molecule B. And then D right here. Draw pentane. 2, 3, 4, 5. At carbon 2 it says to add 2 methyls. Like that. Okay. So now that we've drawn all the structures there, we can now kind of reread what the question is asking. Which of the following compounds only has primary and secondary carbons? Okay. So those are all primary and secondary carbons. That's a tertiary carbon. That's a quaternary, tertiary, quaternary. So those are all out. So the only answer that's possible would be C, which is pentane. Okay, so answer C. What is the relationship between the following two compounds? Well, we need to first establish, hey, do they have the same molecular formula? If we look at that, there's 1, 2, 3, 4, 5, 6, 7 carbons. And how many hydrogens? And we'll count those with the red. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 hydrogens there. If we go to the other side here, we have 1, 2, 3, 4, 5, 6, 7 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it has the same amount, it has the same molecular formula. Okay. Now, are they superimposable? No, they're not. If you can't see if they're not superimposable, then here's another option for you. Okay, so if they're not superimposable, that means they are not identical. So that one's off the table. Okay. Constitutional stereoisomers is different orientation in space of the substituents. We've already established that they can't, well, let's see here. Not isomers, different compounds. Well, they are isomers of one another because they have the same molecular formula. It's just, are they stereoisomers or constitutional isomers? And what we can see is if you name the molecule, okay, if we name this guy 1, 2, 3, 4, this would be 2, 4, no. 1, 2, 3, did I miscount? I did. That's 1, 2, 3, 4, 5. So that's 2 methyl, 3 methyl, dimethyl pentane. And if we name the other molecule, that'd be 1, 2, 3, 4, 5, 2, and 4. So that would be a 2,4-dimethyl pentane. So a constitutional isomer has, constitutional isomers are two compounds with the same molecular formula but different connectivity. And one way to discover the different connectivity is by naming the molecule. If the names of the molecules are different, then they are going to be constitutional isomers. Okay? Now, if they're the same name, then we're going to have stereoisomers. And now when you name stereoisomers, how do you distinguish between the stereoisomers? That's where you use the R and the S configuration. So what is the relationship between these two pairs of compounds? So when you see a problem like this, it's basically saying this is an apple, this is an orange. You're making that comparison. You can't do that very well. So you have to convert one of these either you have to convert this to a chair or convert that to the skeletal structure. It doesn't matter which one you do whatever one works best for you. So I'm going to take that chair and just convert it into the skeletal structure. And I see this carbon right there, okay? 1, 2, 3. It's a 1-3 relationship there. I see that the first methyl that I looked at, this guy right here, it's pointing up on that carbon. And so I'm going to say that methyl is up. Okay? And if we go counterclockwise here, 1, 2, 3, 1, 2, 3, then that methyl right there is also up. That's a wedged. And so when you compare that structure now to that guy right there, you will see that they have the same molecular formula, same connectivity, but the orientation of we have two wedges here versus a wedge and a dash. And so now we have to figure out, are those stereo? They're definitely stereoisomers. Okay? But I want to take this question to another step. So we've just figured out that they are stereoisomers. Okay? But are they enantiomers or diastereomers? Those are diastereomers because they are not superimposable and there's no mirror image. Which of the following is the most stable conformation of the following compounds? First thing, that's our reference point. I would like to just draw the chair myself to make sure we have everything going on correctly here. And I'm going to call that carbon 1, 2, 3, and 4. So 1, 2, 3, and 4. Okay. I see we have an up OH. We have a down chlorine. So that's be like this. And then 3, 4, and then a down chlorine like that. Okay. And when I look at that chair that I just drew, I notice that each one of these groups are equatorial. And that's the most stable conformation you can have with a chair when they're all in the equatorial position. So if I did the chair flip on that guy, they would all be axial. So the correct answer for this guy would be right there. Question 7. Which of the following chair conformations represents trans 1,3-dimethylcyclohexane? What I like to do is just draw it this way first, the skeletal form. And then it says a 1,3 relationship. And it says we have a dimethyl. It says we're going to have a methyl at position 1 and another methyl at position 3. We can see if we count 1, 2, 3. But there's the trans right there. It's telling us the stereochemistry amongst these guys. And it says they're trans. So in order for that to be trans, then one has to be a wedged methyl and one has to be a dashed methyl. Okay? Because those are going to be on opposite sides of one another. So what would be the correct answer there? If we take this structure now and convert it to a chair, we can see in structure A, those are both axial. So those, but that's in a what? 1, 2, 3, 4 relationship. So that's out. That's a 1, 2, 3, 4 relationship. That's out. This is a 1, 2, 3 relationship, and this is a 1, 2, 3 relationship. So with molecule 3, what do we have? We have equatorial here and equatorial there. In the other structure, what do we have? We have axial and equatorial. Now, does that tell us if they're cis or trans? Not necessarily. So let's take a look at it this way. So we have a hydrogen coming off of there and a hydrogen coming off of there like that. Another hydrogen and an equatorial hydrogen there. Okay, I'm drawing in the hydrogen so we can see a little bit better because we need to figure out those substituents if they're up or down. Okay, so this equatorial bond right there, that is down. And then this equatorial bond right here, that is also down. So because they're both down, that means they're going to be cis. So that structure that we're working on would look like this. But then when we look at this axial bond right there, that is up. And then this equatorial bond here is down. Because we have one up, one down, and that means they're trans, because we'll have one of the up carbon will be the wedge, and the down carbon will be the dash. So question 7, the correct answer is D. Okay. Which of the following cycloalkanes has the most angle strain? You know, we just look at the shapes there. The ideal bond angle for an sp3 hybridized carbon is 109.5 degrees. So the one that has the bond angle that's the farthest away from 109.5 is going to be the most angle strain. So that would be the pentipropane. Which of the following conformers has the highest energy? Locate the largest groups that are on the front carbon and the back carbon. That's the trick. Those are what? Are those eclipsed, gauche, or eclipsed? Those are anti, because the bond angle between those two groups is 180. So that bond angle from all the way there to there is 180 degrees. So that makes that the most stable for that. Okay, so now we have, I think they're trying to represent that as eclipsed. Okay, and the two methyl groups are eclipsed. These two methyls right here, okay. Oh, let's look at that issue there. When I circled these two methyl groups, do you see how they're both on the back carbon? That's not the comparison we're trying to make. We're trying to make the comparison between the largest group on the front carbon, which is the dot, and then the back carbon, which is the circle. And so when we look at it from that perspective, we have the largest group on the dot, or the front carbon, is the methyl. And the largest atom on the circle is that methyl. And then what's the relationship between those two largest groups? And those would be eclipsed. Okay, this right here, we're not really comparing the same structure right there. So if you what we could say though, what's the relationship between that guy and that guy? Those are eclipsed. But between these two eclipsed, which one would be higher in energy? It would have to be, this guy would be higher in energy because you have two larger groups that are eclipsed versus a large group and a small group. Okay. And so then, clean this up a little bit. If we take a look at that methyl that's on the front, that methyl on the back there. Okay. So that molecule is eclipsed. Okay. But what's the bond angle between that methyl and that methyl right there? Okay. That would be, well, let's clean it up. that would be 120 degrees. Okay. So based off of this analysis, this guy would be the lowest in energy because the two largest groups are anti. This guy's just not even an option. Well, you know, no. So that's not even an option. So now it's just really the comparison between those two. Let's see here. Because those are eclipsed, the two largest groups are eclipsed, that would make that guy the highest in energy. So the answer is B. Which of the following is not a conformer or butane? So this one you have to be able to take a Newman and convert it into a skeletal structure, if you'd like. And so let's just randomly pick one. Let's do that one. What do I do when I see that? I'm finding the longest carbon chain, okay? So I see this carbon right here, and then that carbon. So we have a CH3, and that CH3 is attached to the dot right there. And on that dot, it's connected to two hydrogens. And then that dotted carbon is connected directly to the circle, which is a carbon. And what is directly attached to the circle? Well, we see that we have two hydrogens on that circle and another methyl, like that. So if we clean that up, what does that look like? Carbon, 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 carbon. That looks like this. And that would be butane. Okay, so when you go through that analysis and looking at all those structures and converting them to something that you can see a little bit better, the correct answer is D. Okay, that is not a conformer of butane. So what is the IUPAC name for the following compound? Let's see here. So we see that the parent chain, okay, the parent chain right here is what? Cyclohexane. The substituents, that one right there is a sec-butyl. That is a methyl. And that is a isopropyl. Now the rule states that you want to give the substituents the lowest locant numbers. And if we count this way, 1, 2, 3, 4, 5, we have a 1, 2, and a 5. What if we actually numbered it this way? 1, 2, 3, 4. So now we have a 1, 2, 4. Okay. Well, what if I tried it in the other direction? 1, 2, 3, 4. 1, 3, 4. So you see that one's off the table there. It's only between the red and the green, and the red one wins out. So the correct answer would be numbering it in the red way, which let's do that. The red would be what? 1, 2, 3, 4, like that. And so what do we have at position 1? We have a sec-butyl. At position 2, we have a methyl. So that's what we will say. 1 sec-butyl, 2 methyl, and 4 isopropyl. Now we just have to put those substituents in alphabetical order. And so we are going to be comparing the B to the M to the I. Because we use the iso prefix in alphabetical order, but sec-butyl, tert-butyl, we do not. So what comes in first in the alphabet? Clearly B, and then I, and then M. So the correct answer is D. What is the IUPAC name for the following compound? In number 12, we have to find the longest carbon chain. I count 8 in that direction. But can I count something something a little bit longer? Nope. Could I have done it this way? 1, 2, 3, 4, 5, 6. Nope, looks like the longest chain would be 8, which is octane. That's the parent. But how do we number this? 1, 2, 3, 4, 5, 6, 7, 8. When do we bump into the first substituent? That carbon 4. Well, what if we numbered it the other way? 1, 2, 3, 4, 5, 6, 7, 8. We bump into the substituent, first substituent, also at 4. So now we have to break the tie. How do we break the tie when we get into this situation? Well, that would be the substituents would help us break the tie. So we have a methyl substituent and a ethyl substituent. And E comes before M. So we're going to have to break the tie that gives the ethyl the lowest locant number. And so that would be numbering in the red numbers. So that would have to be a 4-ethyl. 4-ethyl, 5-methyl octane. And so the correct answer is D. Which of the following is the correct definition for the enantiomers? That is D. Which of the following compound is a Meso compound or a Meso? I've heard it pronounced both ways. So in order to do that problem, we are going to have to draw out all those structures, really, and draw out all those structures. And so you draw all those structures and you will find which ones are which. So I'm going to show you the correct answer, which is C. So let's just draw that one, okay? So we have a dichlorobutane, a 2,3-dichlorobutane. So butane is 4, 2, 3, 4. And then it says to put a chlorine at position 2 and a chlorine at position 3. Okay? But we have to, it told us R and S. Okay? So let's go 1 to position 2. So if we want this to be a R, then we're going to want to go in the clockwise direction with the priority groups. Okay? So what are the top priority groups? Well, that would be the chlorine is 1, that carbon 2, and that 3. Okay? So if we want to go in the clockwise direction and keep that R, then we would have to make that chlorine a wedge. Now, if we go to, go to the third carbon here, number 3, is that going to be a wedge or a dash? Well, if we prioritize things, that'd be 1, 2, 3, and we want it to be an S, okay? So, but the numbers right here go in the clockwise direction, making that R. So if we want that to be S, then we would have to give this guy a dash. Because if it's a dash, we notice that the lowest priority group, the hydrogen, is a wedge. And in those situations, we just trace the higher priority atoms, trace them. It's going in the clockwise direction, which is an R. But because the lowest priority group, which is a hydrogen, is a wedge, we will just take the opposite. And so that is that. And so now we've drawn the molecule, and we haven't even answered what the question wants. So if we clean that up like this, a meso compound is one that has a plane of symmetry. Now this one's tricky because that molecule that I drew does not have a plane of symmetry. But then how can it be meso? A meso compound has at least 2 stereocenters and a plane of symmetry. We have free bond rotation around that single bond. So when we rotate these groups right here and rotate them down, look at what happens to the chlorine. Now do you see a plane of symmetry? Right down there. So that is a very, very tricky problem. Okay. There was a lot involved in that one. If a mixture has a percent EE of 90%, what is the percent of the enantiomer? So that's simply meaning that if we have 100% of a solution minus the 90% EE, that's going to mean that we have 10% that is racemic. And racemic is going to be the racemic mixture is going to be made up of the 2 parts, the positive enantiomer and the negative enantiomer. And since a racemic mixture means it's a 1-to-1 ratio, so that would have to be 5% of the positive, 5% of the negative. Okay. And so what we have, then if that's, what's the percentage of each enantiomer? Well, we have 90% in excess. And let's just say 90% excess in the positive enantiomer. So we have 90 that's in excess plus the 5 that's racemic. So that makes that 95%. And then what's left over? That piece. So it's a 95 to 5% of each enantiomer. So that would be answer A. Which of the following compounds is identical to compound A? Let's see here. We have compounds 1, 2, and 3. 1, 2, and 3. So we just have to see their relationship. And so we've learned that identical compounds are going to be superimposable. So if I take molecule 1 and I want to rotate it 180 degrees so I can get this backbone to match. And if I rotate it 180 degrees, molecule 1 is going to look like this. Okay. No, it's not like that. We'll have the ketone that flips to the other side, but look at what happens to that group. When you flip it 180 degrees, that's now going to be a wedge. And so that molecule right there is not superimposable upon A. So they're not identical. Okay, so that's not identical. If you take molecule 2 and you flip it 180 degrees across the horizontal axis, and so you would make it look like this, and just like that. If I flipped it like that, and then if I took that molecule and flipped it 180 degrees on the vertical axis, I would get this. And now you can see that that molecule right there will superimpose directly upon A. So we've learned that molecule 2 right there is identical to molecule A. Okay. Now if we try to figure out this guy right here, it's just drawn in a weird way. We could just redraw it like this if we wanted to. Okay, saying the same thing right there. Oh, and we have to put our BR on it. And we already said that this compound's not identical to A, and that are identical to one another. And so the only correct option would be is A. What is the relationship between the following compounds? Well, I always give myself 2 check boxes and ask questions about, are they mirror images and are they superimposable? If they're mirror images and not superimposable, then they're enantiomers. If they're not mirror images and not superimposable, then they're diastereomers. Okay. So one thing about this is they're not constitutional isomers. Yes, they have the same molecular formula, but they also have the same connectivity. So they're not constitutional isomers. Constitutional isomers have the same molecular formula, just different connectivity. So the correct answer here is diastereomers because there's no mirror image and they're not superimposable. So which of the following structures in question 18 has the S configuration? Okay. So if we take a look at structure, let's take a look at structure 3. We'll start off with that one first. We prioritize carbons 1 or chlorine 1, 2, 3, and 4. We trace the numbers 1 through 3. And we see we are going in the counterclockwise direction, which makes it an S. However, we have to pause and see that the lowest priority group is a wedge. So when that is the case, we take the opposite. So that structure right, or that molecule right there has a configuration of R. Now, molecules 1 and 2, those are buggers because the lowest priority group is in the plane. So we have to rotate the molecule or draw another one and use that to help us figure out the configuration. I like doing the switcheroo trick, and so I know I want to have the lowest priority group on the dash. So I'm going to switch those 2 groups and draw a completely new molecule. So the H would go there, my wedged methyl, and then our ethyl group right here. If we prioritize that would be 1, 2, 3. We're going in the clockwise direction, so that makes this molecule R. And because this molecule that I just drew is R, and that came from this guy, then that has to be the opposite. So that has an S configuration. And when you do that same process to this molecule here, you'll find that that is also an S as well. So the correct answer is that guy. How many stereogenic centers are present in fructose? We're just trying to find a carbon that has 4 different groups. X, Y, Z, and let's just go P. 4 different groups, okay? So if I take a look at this carbon, that carbon has 2 hydrogens, so that's not it. That carbon only has 3 groups attached to it. This carbon has a hydrogen, an OH, this piece, and that piece. So that is different. So we have 1. Clean it up again. Let's go down to this one right here. It has hydrogen and oxygen, that group and that group. And those look different. So that's 2. And then if we come here, the hydrogen, oxygen, that group, and then that group, that looks different, so that's 3. So the correct answer is 3. Because if we keep going down, that carbon, well, it has 2 hydrogens, so that can't be a stereocenter. If we do that again with this guy, we will see that that's stereocenter, that's a stereocenter for 2 of them. Which is the following molecules achiral. For a molecule to be achiral, it needs to have at least 2 stereocenters, and it has to have a plane of symmetry. Okay. So when we look at these molecules here, sorry. What I just said right here, that's for the Meso compounds. A Meso compound is going to have a plane of symmetry, at least 2 stereocenters, and because it has a plane of symmetry, it makes it achiral. Okay. But this problem is asking which molecule is achiral. So the easiest way to do that is just find a plane of symmetry. If there's a plane of symmetry, it's achiral. So that's achiral. There's no plane of symmetry for that guy. Let's see. There's a plane of no plane of symmetry for that guy. But there is a plane of symmetry that cuts that guy right down the middle. That makes each half identical. That's what planes of symmetry. So if you compare this half and that half, you will see that they're exactly the same. If you look at this half and that half, they're identical. So 21 is C. And the last one right here, what's the relationship between these 2 compounds? Well, if you look at the molecular formula, you will see that they have the same molecular formula. Okay, but what's going to get you tripped up here is look at that methyl and that methyl, but you also have that methyl and that methyl. So you can take this molecule right here, okay? Take that molecule right there and rotate around this bond right there, and you will get this molecule right there. And now look at that molecule in red. You will see that that and that are identical. So answer A.